Okay, so we are going to start here with kind of an upscale process. And we're going to start with that get it together problem you did in class a couple days ago, where you had to balance the equation. You looked at the picture, you tried to figure out what you can make. I think almost all my groups opted to do this by kind of the lasso picture method, which is fine. But if we had decided to do a BCA table, this is the BCA table that would have gone with that situation. The reason that I've got this drawn here is that I want us to, again, kind of take note of the ratio idea. My balanced chemical equation is a 1 to 2 to 2 to 1 to 1 ratio. My change row is 3 to 6 to 6 to 3 to 3. That is the exact same ratio as what we have in our balanced chemical equation. And so right here, we're just going to leave ourselves a little note. And our little note says that the ratio here matches the ratio in the chemical equation. It's going to become sort of the check row to check and see how you're doing. The other new thing that's shown up is this MLCS. This is an abbreviation for molecules. It's going to become important what the units are on the numbers in your BCA table, and I needed an abbreviation for molecules, and so I came up with MLCS. I know it seems obvious that we should use MOLE or MOL. We're going to need those for something else later, so we can't use them for molecule because chemistry basically already has taken that and used it for something else. So for now, we're going to use MLCS for molecules. Even when we upscaled this process, if we look at the change row right here, we're expecting a 1 to 2 to 2 to 1 ratio. You see the 34, 68, 68, 34, and 34. And again, ratio matches chemical equation. And that's what we're going to put down here in what used to say important observation right before I poked a hole in your paper, and now it doesn't say that anymore because I poked a hole in your paper. But for our important observation here, we are going to observe that the ratio in the change row matches the ratio in the balanced equation. And so constantly, I want you to keep that in the front of your brain, and I want you to always be checking your change row to make sure that that ratio stays the same. The other idea that has emerged through lots and lots of these problems is the notion of the limiting reactant. The term limiting reactant is the term we have for the reactant that runs out first. When it runs out, it causes the reaction to stop. In other words, it has total and complete control of the outcome of the reaction. This is the controlling factor in the whole entire thing. We're going to work a couple of examples together. And then at that point, it just becomes a task of practice, practice, practice. So, some BCA table examples. Okay, at this point, we have two rules. Rule number one, the numbers in the chart must count particles, not mass. So you can't put grams in there, you can't put AMUs in there. And it's because our BCA tables are a substitute for the pictures. The pictures were counting particles, so the BCA tables have to count particles. Rule number two, changes in chemical reactions are going to occur at the ratios given in the balanced chemical equation. That was the idea of your change row must match your chemical equation. Okay. At this point, if you are writing in pen, I want you to switch to a pencil because we may hit a moment that we want to erase. All right, here we go. How many molecules of NH3 will be produced by the reaction of 5,325 molecules of N2 and 14,022 molecules of H2. We don't have any of this, that's why we're trying to make some. Now, we just went well beyond the point of you wanting to draw a picture even if you didn't know what was going on. Like, the picture can bail you out on a small scale. We're to the point now where that would be an awful, awful picture to draw. And so we're going to count on our BCA table. Well, here we go. Let's just give it a shot. I'm going to spend 5,325 molecules of N2 down to 0. Okay, so I'm going to use it all up. Now I have to think about this box. It is a 1-to-3 ratio in the balanced chemical equation. My change row needs to be a 1-to-3 ratio. I want you to think about whether the number going in here needs to be bigger than 5,325 or smaller than 5,325. Give me a thumbs up if you think the number's got to be bigger, and a thumbs down if you think it's got to be smaller. Good. If we're going to maintain a 1-to-3 ratio between here and here, this number has to be 3 times bigger. So when I spend hydrogen, I'm going to spend, and I'm going to write it as 3 over 1. 3 over 1 times as much as I did of nitrogen because of the 3 here. 5,325 molecules. Okay. Now we get out our handy dandy calculator. 5,325 times 3. I'm going to spend 15,975 molecules. Now, am I going to spend 15,975 molecules? Why am I not spending that? You don't have it, and chemistry doesn't run on credit. All right, erase. It didn't work out. So we're not doing that. This is going to happen to you. You are periodically going to have to erase. You may eventually get to the point that you can kind of make an informed decision about where to start. But even then, you're going to sometimes have to erase. All right, this problem, take 2. Let's spend 14,022 H2 molecules. And try that. Okay, now we got to think about this box. If I'm spending 14,022 H2 molecules, give me thumbs up if you think the nitrogen box needs to be bigger than 14,022, and thumbs down if you think it has to be less than 14,022. Good. It's got to be less than, because we have to maintain a 1-to-3 ratio. It's only going to be 1/3 as much. 14,022. So let's try that. 14,022 divided by 3, I will be spending 4,674 molecules of N2. Is that okay? Yeah, I can afford that. I have 5,325 of those. I'm going to spend 4,674, leaving me with 651 molecules left over. I spent all of the 14,000 molecules here, and I just determined that H2 runs out first. H2 is my limiting reactant. It's the one that runs out first. As long as we're on that thought, the opposite of limiting reactant is called the excess reactant. And it's going to be N2. It's the opposite one because I have excess of it. And I'm going to label this column up here, limiting reactant. Now we just got to finish the process. So now I need to think about this box. Because the limiting reactant has control of the situation, we're going to do everything relative to this 14,022 particles here. So I want you to think about this box. We're trying to decide bigger than 14,022 or smaller than 14,022. Thumbs up if you think it's going to have to be bigger. Thumbs down if you think it's going to have to be smaller. Okay, good news on the thumbs down. Because 2 is littler than 3, the number that goes in the box with 2 has to be littler than the number that goes in the box with the 3. I'm gaining NH3. And I've got to use a fraction using 2 and 3. But if I want that number to end up smaller, I have to use 2/3 instead of 3/2. 3/2 would make it end up bigger. A little bit of calculator work later, and I figure out that I'm going to gain 9,348 of these molecules. And I'm actually going to pull this negative 14,000 down here. Because if these three numbers are all in a row, it's really easy to check myself. I have to have a 1 to 3 to 2 ratio. I can kind of look at these and try to figure out 1 to 3 to 2. Yeah, that looks pretty good. You could use your calculator to check it if you want to. But some other things you can check on. This is the one with the smallest coefficient. Its box better have the smallest number in it. And it does. This one has the largest coefficient. It needs to have the largest number in it. And it does. This coefficient is kind of in the middle. This number is in the middle of the other two. All right, I feel pretty good about my change row. Your change rows are going to have to start to be twice as big as everything else. So when you start to practice, I want you to draw your change rows as being double tall. We are going to add a science practice target at this point, which is science practice 1, which is an ability to communicate your thought process. You are going to get a color for science practice 1 based upon what's going on in your change row. I want you to show your fractions and your numbers. I want to be able to see what you're thinking in that change row. So your change row needs to be a double tall row with fractions in one and then the numbers down below. Okay, so that means that with all those ratios looking good, 9,348 molecules. And now we need to know how much it's going to weigh. This is a periodic table question, so grab your periodic table because you're going to have to calculate how much an NH3 particle weighs. So we have 9,348 molecules. If you add up a nitrogen and 3 hydrogens from your periodic table, you get 17.031 AMU. And we come up with 159,205.788 AMU. For now, our rule is going to be that since your periodic table takes the mass to 3 decimal points, we're going to keep masses to 3 decimal points. We are going to, over the next few weeks, start to establish some rules about how to manage these numbers in your calculator. And so our first rule is, in dealing with these masses, keep them to 3 decimal places because that matches what your periodic table is doing. Okay. There we go. We went bigger, all the way to the point that a picture would be a completely impractical way to go about doing this. All right, with your team, I want you to start working your way through number 2. I'm going to periodically add things to mine. So if you get stuck, you can pop your head up and see what I've put into mine to try to get yourself going again. So work with your partners on this. Just fix your calculator. Do second function science or yeah, just switch it back. right, and once you're done, I want you to dig in your backpack and find as many colors of highlighter as you can find, and or colored pens, and or colored pencils, or crayons, or anything that you have lots of colors of. We're going to do a little highlighting and annotating here. So you need lots of colors. Five would be ideal. I might have to get to 5. I think I'm going to have to use some yellow. Okay, let's take a look at a few things here. First of all, question 2 introduced you to the concept of excess. How exactly you manage excess is a little bit up to you. Some people just literally write XS in this box for excess. I always put lots because to me that's a reminder, like I have so much of this that it doesn't really matter. What you put in the after, a little less than lots, lots minus 486, still lots, still excess. It doesn't really matter too much as long as whatever you do is recognition of the fact that there is so much available that it doesn't have control of the process. Automatically, if one of these is in excess, the other one is going to be the limiting reactant. So this one, I think once you got going, shook out pretty well. You spent 486 molecules, but you had a whole bunch, so it doesn't really matter. And you ended up with 31,135.104 AMUs. For some of you, you're thinking, I've got this. I totally understand what's going on. I'm ready to rip forward at this point in time. Others of you are a little hung up in the details at this point, and that's all right. We're going to try to add some color here for those of you who are still kind of bogged down in the details. So, some important ideas. Important idea number 1 is the limiting reactant idea. The limiting reactant has control of the process. That's why in the change row, this 14,022 that went with the limiting reactant appears in every single box. It's the limiting reactant controlling the process, and if that's what's controlling the process, that's what shows up in all the boxes. The same thing happens down here. The O2 is the limiting reactant. We're spending 729 molecules of it. That 729 is going to show up in every single box because it has control of the process. The other significant thing about the limiting reactant is that the coefficient on the limiting reactant is going to show up in the denominator of every single fraction. One batch of this is per 3 H2s, and that idea, per 3 and per 3, shows up in the denominator of every fraction. The coefficient on the limiting reactant shows up in the denominator of every single fraction. The other number that shows up in that fraction is the number that comes from that box. The number in front of this nitrogen is a 1. That becomes the numerator in the N2 box. The number in front of NH3 is a 2. That becomes the numerator in the NH3 box. Now, I started this process by having you think about would the thing in this box be bigger or smaller than the thing in the limiting reactant box? And I think there's something to that bigger, smaller idea. Like knowing that we needed to do something with the 2 and the 3, our options being 3/2 and 2/2. And if I want it to be littler, I'm going to use the 2/3 part. But it is also useful to kind of have some color coding in here to see where I got those numbers. Jumping down to the next one, the number in front of the H2S becomes the numerator. The number in front of the SO2 becomes the numerator. And the number in front of the H2O becomes the numerator. And so there's some color coding to help you kind of track where I got the numbers. But I continue to believe that thinking in terms of bigger and smaller is really the way to go. Do I want this number to be bigger? Do I want this number to be smaller? At this point, it becomes really just kind of an issue of practice, practice, practice. So I would like you to come up at this point and grab a copy of our practice sheet.